Good evening, everyone. I'm happy to be there. That is the first time I'm going back in the conference in 3D now. So that is a good thing. So thank you also for the invitation. So what we would like to address today with you, it's not... we start working on this problem quite a long time ago in order to bring decision support tool to the pilot, in this case, in case of emergency. So I will give just a brief agenda of this talk. So I will present the objective of this work. My student, Andrea, will present the resolution algorithms and some results we have developed in this research. And we will address conclusion and perspective. One thing we have to mention, sorry, I have to be close to the mic. This work is sponsored by the Clean Sky project with Thales Avionics FMS division, which is also involved in this research. So, what is the objective of this work? So, if you go to history first, I will introduce the FMS. So, the autopilot is an old system now, but I remember when I was a student in 1992 at ENAC with the A320 flight, we were able already by using these tools to do a kind of automatic flight from Toulouse to Paris-Charles de Gaulle. Only though the aircraft was moving out from the road of the aircraft. And this system is also in charge mainly of the landing, of the maneuver. For instance, when you do a landing, the Civil Aviation Authority, the airline, and the aircraft factory, a Boeing and Airbus, ask the pilot not to touch. So in addition to these things, the FMS has been developed for managing the navigation of the aircraft to optimize the trajectories. And more AI is coming in this system now to give decision support tool for the pilot. And even more in the future for the young guys, I think for the SPO operation, single pilot operation. So the intelligence of the aircraft will be more and more in this system. So the tool we expect to develop is to be included in this system to propose alternate in case of emergency. So I give you some example of critical situations. You remember this crash in 2009. So it is a very famous event because there is an happy end. So due to bird strikes, the aircraft lose both engines. You know this story. And in fact, the aircraft, just a minute, I try to see if I can, yes, here. So take off from LaGuardia, at the bird strike here, and as you know, the aircraft glide to the Hudson River. But if you see the timestamps here, you see at that time, so about 1527, and they reach the water at 3:31. So roughly we have 3 minutes gliding. So in this case, we were working on this work, on this crash with Georgia Tech with Panos Chotras in 2009. The idea was already to propose alternate to the pilot in case of emergency. The pilot could say, I accept or refuse, but the system is able to propose something. So that is the real purpose of this work. So I put also some other, so this one is the most critical one because you are close to the ground and you have very short time for proposing something to the pilot. I give you also two other cases. So the Air Transat flight 236 in 2001, Toronto-Lisbon. So due to a fuel leak, the aircraft ran out of fuel, so it glided for 120 kilometers, 21 minutes, so it was much higher, before reaching the Arthur Island. This one also, we was working on this crash with Georgia Tech in Swiss Air flight from JFK Geneva due to fire on board in 1999. The pilot was unable to reach this Halifax. But in this case, you have 14 minutes from the event to the ground. just to remember, over 70% of fatal aviation accidents are in the takeoff and landing phase because of you are close to the terrain. In some area where you have mountain, it is even more critical. You have to take into account weather. So thunderstorm, for instance, when you have an event like the previous one, you have to be able to reach the ground, avoiding the mountain and also avoiding the weather. And you have to take into account the wind, because the wind may be depending on the direction of the wind and the direction of your heading and the landing site you select, you may be able to reach or not this landing site. So we have two types of emergency. So the as soon as possible, which is the ASAP, most critical emergencies, the pilot has to find the fastest way to land. So it could be linked to a cabin fire or depressurization. And another class is at nearest suitable airport, which is called ANSA, which must be a safe landing, for instance, when you have dual engine failure and things like that. So we will come back on that in the result. And the time is the most critical factor. So I remember for the US Airways 1549, 3 minutes. So we have to develop a strategy which gives advice to the pilot in a very fast way. So that is the main purpose of this work. Fuel may be a limiting factor too, depending on your emergency. So the challenge is the real-time requirement and the convergence guarantee of your algorithm. You are an aircraft here, you have different landing sites, which are proposed by another algorithm in the project, and we have to produce safe trajectories to bring back the aircraft to the ground safely. So we can address that with a classical optimal control approach, but in this case it is too long. The right approach is to do that, to produce these trajectories in two phases. The first phase will, what we call the geometric planner, that is what we have mainly designed. So we try to design the 3D path. When you have designed this 3D path, you do the time parameterization, which is called the motion planner. Doing that in two phases, it is much efficient in terms of computation. So the key idea is first find a flyable path, that is what we're doing here, to avoid obstacle, weather, and things like that. Then find the flyable trajectories with the time to follow along this path. So some previous related works I just mentioned here, so the one with Fallas. So in this case, we avoid the terrain, but the critical issue is here, the computation time limitation. Another thing that is the one we did with Georgia Tech, so it is the Hudson crash here. So the idea is to bring back the aircraft here. It is based on this hierarchical approach, but do not take into account obstacle. So what we propose in this work is to bring all the advantage, but with the computation efficiency. So I give the floor to Andreas to describe this algorithm.
Thank you, Daniel, for your introduction. Good afternoon, everyone. So I'm going to present you the algorithm which has proposed to solve this problem. Firstly, what are the objectives of this project? The first main objective is to find a safe, flyable trajectory. It's not necessary to have the optimal trajectory, the fastest trajectory or the shortest trajectory. The second objective is to take into account the type of emergency, so ASAP or ANSA. And the final objective is the most important objective, is to have a very efficient algorithm in terms of computing time. We have a very constrained problem. So you can see the different constraints. The first constraint is a heading constraint. we have to take into account the direction of the aircraft at the moment of the emergency, and also the landing site direction. Of course, the trajectory has to avoid the obstacle. So there is two types of obstacle, terrain and river obstacle. Depending on the type of emergency, the curvature and the descent profile can be very different. For example, in case of dual engine failure, the aircraft has to descend to keep a sufficient speed to avoid stalling. So we have to take into account the descent profile and the curvature, mainly defined by the radius turn and the number of turns. And the final constraint is the wind, so we have to take into account this. So we want to have a very efficient algorithm to generate the trajectories. So we decided to use the algorithm called Rapidly Exploring Random Tree. It is a sampling-based path planning algorithm. At each iteration, a new random point is generated in the space, and if a connection is possible, you create an edge. So a connection is possible if there is no obstacle between the two points. At the end, you can connect the final point, so for us is the landing site, to the graph and generate the path. So the main problem of this type of algorithm is that the computed path is not flyable because you can create discontinuity of heading, and so it is not flyable. To solve this problem, we decided to connect each point by a single turn curve composed of a first turn to the right or to the left, and then a straight line. So phi is the angle of turn, and L the length of the straight line. So I'm going to present you the algorithm in 2D, but keep in mind that the aircraft is descending and following a descent profile. So at an iteration, we generate a point, a random point in the space, here the red point, and we connect this point with a curve. And with this curve, we can determine the new heading of this point. We repeat this procedure for each iteration, and at the end, we have a graph of curves. And finally, we can connect the final approach point to the graph, and finally, we have the trajectory. Now, I will give you the objective function of our algorithm, where we want to minimize something, and we decided to minimize the curvature of the trajectory, because in case of emergency, we want to limit the number of maneuvers, and so limit the turn of the aircraft, the turns of the aircraft. So for trajectory, composed of n curves, we define phi e the turn angle of the curve CE, and we decide to minimize the sum of the exponential of each turn angle of the trajectory. So, for example, there are two trajectories, and we prefer the green trajectory because there is only one turn, and whereas that the red curve is composed of many turns. So we penalize this type of trajectory. Now some results of our algorithm. We tested our algorithm with Airbus A320 with an emergency declared to Grenoble, near to France. near to Grenoble in France, sorry, because it's a very interesting case, because there are many mountainous obstacles, and we tested with two different cases, ASAP emergency and ANSA emergency. So the emergency is declared near to Grenoble at an altitude of 32,000 feet. For an ASAP emergency, our algorithm generates 11 different trajectories from the emergency position to the landing site. The landing site selector generates landing site near to the aircraft position because we are in ASAP emergency. The vertical profile of one of these trajectories, you can see that there is a very fast descent to reach the Grenoble airport. In the case of ANSA emergency, the landing site selector generates landing site near to the aircraft position, but also airports very far from the aircraft position, because we have time to land. So, for example, we generate a landing site at Marseille or Toulouse. And in this case, we generate 11 different trajectories. So the profile of the trajectory from the aircraft position to the Toulouse airport. We can see a very long cruise phase and then the descent. The main objective is to have a very efficient algorithm. So our algorithm generates 10 trajectories in 10 seconds for an ASAP situation, and in 15 seconds for an ANSA situation. This difference of computing time can be explained by the fact that for very far airports, we have to define a specific tree, LRT, and so that can increase the computing time.
So just finish, just to complete what Andrea mentioned. So why we decided to minimize the number of turns? It is a recommendation for liner who is also my pilot who is in the project with us. Okay, because at the beginning we didn't put. So just to conclude, so as you can see, emergency is a huge. We want to reduce the workloads for the pilot, so we need new DST for this kind of stuff. But I think in the future we'll need new assistance for the pilot, mainly for the SPO. We propose an efficient algorithm. So roughly for one trajectory, we compute this trajectory in 1 second. So quite efficient. And so it has been extended with a landing site selector. So for instance, on the way of the aircraft, we have a landing site selector. The system computes in real time all the way, all the trajectories, and when, in case of emergency, the pilot selects a request, and the system will give him some proposal. It could be accepted or not, like I said at the beginning. So we will try it on real test case in the future. So this also, it is a good application for the UAV. For VTOL, we have the same problem, for sure. And on an extension, also, we use the same algorithm to design the seed star around the airport. So this is another application we are working on now. So, have you got some questions? We are happy to answer if you want.
Well, thank you very much. I really enjoyed the presentation, because you proved that, well, artificial intelligence is not just data and neural networks and reinforcement learning algorithms, but sometimes smart algorithms like the one that you propose can do very complex tasks in a very short amount of time. Eh? So, first of
No,
all,
yes, I'm coming from AI, but you know, AI is wider than machine learning, and in AI you have also decision support tool, and more in this side.
So I also like this kind of algorithms. So my question is, the random points are uniformly distributed, or you bias the generation of points close to the feasible space?
So this morning was talking with the student because we don't know exactly the worst time, but we remove one slide. Yes, there is a bias close to the landing site for sure.
Okay. And then my second question is, this is just the generation of the trajectory, no, right? But then the motion planner includes the thrust and speed brakes, or you are assuming either thrust?
So no, the motion planner, it is so we deliver the path, and the motion planner is computed after with the time parameterization by Xavier from your university.
Okay. Well, my former university.
Former.
Yeah.
Yes, you are not a student anymore, like me.
Okay. Thank you, Daniel.
Other question?
It's me. Thank you very much. Very, very interesting topic. I would like to know, do you have some idea of how the user experience would look like?
Sorry?
Would it be what the user experience would look like? So would it be calculate a path every 10 seconds, and then there's just one button you'd press in the case of an emergency, and then it would directly put that into the computer?
The computation is not done on a request. The results are asked. It is done on real time, always. Mm-hmm. So your aircraft is moving. You check the landing site. It could be airport, field, or any other surface. It could be also water. And it computes on the way. And if it is needed, just press the button and could say yes or no, depending of. He's still the pilot, but just propose something.
Cool. Thank you.
Thank you very much for the presentation. I have a question. I know that each case is different, but because they are following all aircraft, they end up following more or less standard trajectories. Can you use a library of possible trajectories to help to have a starting point for the computation of the final trajectory and to speed up the process?
We could, but we have two issues about that. First, it means in any place on the planet, you have to have such a backup offline trajectory prepared. So I think it is. We didn't go in this direction because we were quite satisfied by the performance of the computation because it is 1 second. And in the project, they request us to do that every 10 minutes, so we have much more time than needed. So, but that is a good idea. It could be also more in some area with Kathmandu. Kathmandu, a lot of mountains. It's just but we didn't use this kind of pre-processed trajectories.
Thank you for your presentation. Very interesting. I'm curious about the objective function. I'm not that sure whether your constraint has considered the altitude dimension. How do you consider this, the altitude change or the speed of it?
You mean altitude?
Yeah, altitude.
So, in fact, in case of emergency, or for instance this one, or you have no engine. Mm-hmm. So we don't want it was a constraint of the project from the pilot. Mm-hmm. We proposed at the beginning that the algorithm could change the slope. And they request us to block the algorithm in order to have a single slope for descent. I don't know. That is from their advice. So we could have included that in the objective function. But from the beginning, they said you will descend with the same climbing descent rate.
Okay, thank you.
They want us to keep as much energy as possible at the end. For this, when you lose the engine, but these are good questions. It could have been included, but.
In the motion planner that you mentioned before, is the weather also coming in there, or where is that coming in?
Yes, so for instance, if we consider this curve, at the beginning, the path generator already take into account these things. So for instance, here, depending on the wind, you will have a different, for instance, if I have headwind, I may have issues to land in a given place. If you have tailwind, this is different. So we take into account this in this path generator and in the motion planner too.
Okay, yeah.
The only things we didn't take into account for the moment is just a matter of data. It's a thunderstorm. But it is like a cycle for us.
An obvious question. What would Captain Sully do with your system? Would he manage to land on the ground?
Sorry?
Would the Hudson River scenario, with this system, would it be possible to land on the ground?
For sure. No, for sure, because already I show you a picture here, this one, which has been done in 2010 with Georgia Tech, but Panos Chotras. It is quite easy. It is easy to do that after. But the idea here is to there were 4 alternate trajectories. So in this case, the landing site is given here, no obstacle. This result, this work here, but you have to be in the cockpit. So no, I prefer to be careful about that. But it is possible, yes. It is not the only work. I saw recently the movie with and there are many studies. Yes, even at Airbus, but in the movie it is with the Airbus simulator. So anyway.
Yeah, thank you for an interesting talk. And this, my question is actually triggered by her question about losing the engines. So, as you said, like it is actually calculating all the time the possible, like the best trajectories, and you push a button even there is an emergency. So, actually, so does it also take into account what kind of emergency you have? Because like even the trajectory which takes more time would be like more safe depending on.
So yes, we didn't mention we have also different kind of emergency. Medical emergency, it is another emergency for which you have all the capability of the aircraft. So you have your engine, but you have to find the nearest port as possible for medical emergency. The worst case is when you have also nothing, no engine. So, but I agree with you, there are some of the failure. For instance, you may have an issue with the rudder. We can't take into account all the possible. We start with that, for sure. We have to start with something, but we can't investigate. For instance, you can consider, we mentioned that one day, if the aircraft is able only to turn right for some reason. But we can't plan everything, for sure. We can't predict the future, never. Today and tomorrow.
Just like, for example, your engine has like 30% of the capacity as compared to no engine.
For us, it is not really an emergency. It is different. We try to tackle this one because it is one of the most critical ones for the pilot. But I agree with you, there are other cases which are not included in this tool, for sure. But the pilot is still there. For the UAV, it's different.